Good morning. Today's topic is Ampere's law, often called in EMF circles as Ampere's circuital law. This is the common terminology which we employ in our EMF. Today we will discuss about the statement of Ampere's law. In the last class, we have seen about magnetic forces on current elements, and now by the end of this lecture, I hope that you will be able to state and explain Ampere's law. Coming to the statement of Ampere's law, it states that line integral of tangential component of H around a closed path is the same as net current around the path. I repeat, line integral of tangential component of magnetic field intensity around a closed path is same as the net current enclosed around the path, which means that let us suppose there is a current so I'll take a path this will be in this direction. Okay. The mathematical expression for Ampere's law is integral of H dl, this is my dl, is equal to I enclosed. So which means a line integral of tangential component. See, whatever the integral which you are considering, this is dl, or the entire length, whatever the flux intensity vector is, field intensity vector is, it is equal to the current which is enclosed by this path. And this path is called as an Amperean path. So whatever the current which is being enclosed by this Amperean path, this is the current, right? This is I enclosed. So this is the equation. Now let us suppose if there are two currents. This is I1 and I2. So in this case, it is equal to I1 plus I2. Okay. So this is the statement of Ampere's law. Line integral of tangential component of H around a closed path is equal to current enclosed by the path. Now, it is very similar to the Gauss law which we have already seen in static electric fields. And this particular law is generally employed to determine the magnetic field intensity in case the current distribution is symmetrical in nature. Now we know that Stokes' theorem is one of the commonly employed theorems for line integrals, right? Stokes' theorem states that NE is equal to, it can be converted into surface integral. Right, so I am applying the same theorem here. Instead of A, I am utilizing here my vector is magnetic field intensity. So this is my application of Stokes' theorem to this one, converting line integral to surface integral, closed surface integral. Now, also on the other hand, I do have I enclosed, right? We know that current elements we have already seen, right? I hope you do remember these are the current elements which I have taken here. So IDL is equal to, I am considering this one, IDL is equal to JdV, or I can write it as I is equal to, I is equal to J dV by dl, I will take it as J ds. So if I am considering this as a differential area, so automatically I need to consider this like this, right? So I can write it as I is equal to, right, over the entire surface area. This is my conversion of this I enclosed in terms of your current density. So now for the Ampere's law, I will apply these two terms for the left and right side. What was Ampere law? This was Ampere law, right? Now this has been modified with the help of Stokes' theorem, and this I have employed current density. If you compare these two, left hand side and right hand side, you can see that del cross H is equal to J. And this particular is called as Ampere's law in differential format. The same, this is Ampere's law in integral format. This is Ampere's law in differential format. And this is also termed as Maxwell's third equation for electromagnetic fields. Try to remember, this is Maxwell's third equation. We have got two equations in electric fields. Now this is the third equation for which is coming from magnetic fields. Okay, and try to remember, if del cross H is not equal to 0, then the magnetic field is not conservative. Try to remember this point. If del cross H is not equal to 0, then the magnetic field is not conservative. Okay. So I hope now you are able to state Ampere's law. It states that. Okay. The line integral of tangential component of magnetic field intensity vector over a closed path is equal to the current which is enclosed by the path itself. So this is your question. I'll be asking for a short answer. And in the main class, we will discuss different problems based upon this Ampere's law. Thank you.